If they're in the right spot, they're less likely to be noticed. Like they're on an edge. Like if you took a picture of me and the outline around me is an edge, if you have your shellcode in that location, because those aren't going to be pixels that are part of what the picture should be, it's going to be less noticeable. Also, just the way that colors are generated in a picture. As I'm sure most people know, you get a color palette by combining a small subset of colors, like red, green, blue. You combine those together in different ratios, and that's how you get your full color palette. And it's the ratio of the perceived brightness of each of those components that gives you the color. It's the weighted average of those components that gives you the brightness. And if you look at the percentages in that example, which makes a gray color, you can fudge with things that have less of an effect on the overall color than other components. So I could mess with the blue a little more than I could mess with the green before it would become obvious. And this is important to us because it allows us to make changes to a picture, and we are degrading the detail in that picture, but it's not that bad. You just think, oh, this person didn't know what they were doing, they did a bad job saving this, they did a bad job of using Photoshop. You don't think, oh my gosh, I'm looking at a bunch of shellcode. These are just some examples to sort of illustrate what I was talking about with psychophysics. So here's an image which at first glance might look like just a uniform color. And if you look at it closely, and it's probably harder to see with the projector, it's actually, the left-hand side is an 80% gray color, the right-hand side is white, and over the entire image, it's blended smoothly. So that helps, makes it look like a uniform color. Here we've only blended over 50% of the image. I don't know how well it's, yeah, this one I can see it. You can see that transition a little bit better. And here, I've done it only over 25% of the image, and it actually almost looks like a hard edge. It almost looks like two different boxes or rectangles. Here's another example. The background of those boxes is different. The bottom one is pure black. The top one is slightly off black. On their own, you wouldn't notice that. You would think that the top one was pure black. Same alternate flip side here. Top one is actually off white. Bottom one is pure white. The eye can't really tell those differences, and that's important to us because it allows us to make changes that aren't as obvious.
Okay, one of the other important things to know is how images are stored. When you got a 2D image, when you see it, the computer only, because of the von Neumann architecture, only sees it as a 1D array of bytes. There's multiple different color encodings you can use. For images like grayscale, for black and white images, and that just gives you it's typically an 8-bit or 1 byte per dot. Red, green, blue, which is like what your monitors use. CYMK, which is for printing. YCBCR, which you might not be familiar with, which is what JPEGs use. It's also similar to what your television uses for the color. And index color encoding, where you actually look up a table of colors and you don't actually store the color values directly in the image, it's all indirect. And with compression, the files themselves can either use no compression, like raw full color bitmaps, or the PNM format, which we use a lot in in the tools. Lossless compression, such as PNGs use the zlib deflate compression, which is the same compression as is used by gzip and also by pkzip's deflate method. And there's lossy compression, which JPEG uses some psychophysics to determine which part, they've determined which parts you don't necessarily need to see. And depending on your quality settings, after performing what's called a discrete cosine transform, which hopefully I can explain in a way that most people will get, if not, it's not all that important, it drops off a little bit of some of the values, and that's how it does the compression on those. And the file in memory is decompressed into a 1D array, which is the width times the height times the number of bytes that it takes to store each color. And then the contents of that can depend on the display color depth. So with your 24-bit color, it takes 3 bytes per pixel, 16-bit 2 bytes per pixel. The net PBM super format, or PNM, is a group of file formats which are used for storing images. On the right, up the top, is the actual contents of an image file. It's a really simple format. The top is the type of file it is. Then the next 2 values are the width and the height. Then it's the maximum value in it. And after that comes the raw data. I've chosen those particular values because the bang is the lowest character you can actually type and see come up on the screen, and the tilde is the highest one. The image underneath that is actually that image blown up a bit. It would be too small otherwise to see. We use this a lot as an intermediate format in the tools that we've developed. Another relatively simple format, but quite a lot more complicated than that, is the PNG, which is got a header for the PNG itself to say the file type, then the image header, then the actual image data itself, which is compressed using the gzip, then an image footer, and every header has a checksum, a CRC32 checksum stored with it. Some other features which are supported and which are useful are the color correction mappings and the transparency. Because, some programs store the colors in 24 bits padded to 32 bits. Sometimes it just puts a random padding value of 0 or FF in there. And that makes writing shellcode a little bit more difficult. We haven't done that for our one, but because it's designed to work in IE. This file here is some random website I went to with, and I downloaded a GIF off it. We converted it to a PNM and scaled it up, so it took up 115 meg of memory. And we passed it through an early version of PunkGUI, which is the tool for converting to PNG that we've got on our website. And it came back as a 1.2 meg file. Now, is it loading? How do I do this? In the browser itself, is it coming up? It looks pretty much like the actual picture that you see on the website. If view image, you see which one I want? Which one's view image? That one?
At the very top.
Okay. This image is actually kind of big, as you can see. It's the full size. Over here, you probably can't see, but there's a few dots there. Yep. Yes. What that is the shellcode. The colored dots are the shellcode, and everything else is NOPs. And you just got to land before the shellcode, or it'll crash off the end. But you can usually hit it though by changing the location of the shellcodes or the image size, and you can just hide it in a place like that where you wouldn't see it.
So to further illustrate it, here's another picture of some guy that we found. I guess he's a hacker. And this first image is just a regular image, a JPEG image. But on the right-hand side is an intensity histogram, and it's on the y-axis we have the relative amounts of each color component, and on the x-axis we have the intensity of the color components. If we convert that image into a GIF, you can see that the intensity histogram changes. A GIF only uses 256 colors in its palette, and so you can see our histogram now has all these gaps in there, and that's because we've gone from many colors to only 256 colors. So in theory, there should be somewhere fewer than 256 bars in there. This next image is actually a no-op sled, and you'll see again there's gaps in that intensity histogram. In this case, there's some bigger gaps. Let's actually blow that picture up and look at it in a bigger. So the one on the left is a regular image. The one on the right is a no-op sled, and you can see the quality is degraded. And in specific things that stand out, look at his arms. Like his right arm looks like he has some nasty prison tattoo on it. And knowing the history, perhaps that's real. I don't know. Above his head, things are a little bit weird. So you can see, and so why are certain pieces of that more degraded than other pieces? Well, the histogram on the last page, you can see there were bigger gaps there. Like right in the middle, there's some big gaps. That's because there's unsafe instructions in there that we just couldn't use. So that's just the reality of this technique. There's certain colors that you're not going to be able to access. So, for example, in one of those gaps, it was that we had opcodes from O by 70 to O by 7F, which are jump short instructions, and we can't touch those because it's going to change code execution. we probably can't touch those. You know, one thing that, a place that you could take this to make it a little more complex, a little more perfect, is that maybe you could use some of the values that we're avoiding. And the reason you could do that is, for example, you could not encode certain portions of the picture. Because again, all you need is a no-op sled and shellcode somewhere. So maybe the top half is that, and the bottom half is still a regular JPEG picture or PNG or whatever it is that you're using. So you could not encode the parts of the picture where you found that you didn't get a good quality image. You also, maybe you could use things like conditional jumps to actually jump around and jump over those portions of the picture which aren't properly encoded and have instructions which aren't necessarily considered no-op. So I mentioned already, now enough theory. We'll show you guys some demos to actually, you know, put this into practice. So we came up with a couple of different tools. I focused on a tool that worked on PNG coding. My job was easier because PNG is a lossless format, so it's not mangling my shellcode. Greg will discuss what JPEG does. It's a lossy version of image encoding, so it's going to mangle the shellcode. So he had to do a lot of extra tricks. So I took shortcuts. So Punkui is the JPEG one. JPEG is the JPEG one. Punkui is a C# application. It's a Windows GUI application. JPEG is command line, and it requires actually some other applications that it works alongside of. Yeah. So this is a video. Which isn't, oh, okay. Sorry, I gotta watch over here. So anyway, yeah. So on the left-hand side is where our original image is going to go. On the right-hand side is where our new image is going to go. So the first thing I'm doing is just selecting the initial image, and this is a real image. It can have you know, any kind of. You can use a JPEG, you could use a PNG, you could use a bitmap file. The original image doesn't matter because we're converting it later. So this is a picture of some guy. I was at a wedding last year, and they put this drunk guy at my table. I think he works for Tipping Point. And this is just the original image. So it's just a JPEG image. So the next thing we want to do is resize that image. And you see the resize in megabytes, 32, 64, 128. You're thinking, that's a huge image. We can't possibly have something usable. That's the size that it will be when it's in the PNM format, which is the intermediate format. And again, we want to make a really big image. We want to make a really big image because the bigger the image, the bigger our no-op sled is, and the less obvious our shellcode is. Fortunately, the encoding formats like PNG and JPEG, they shrink it right down so that 128 or 32 meg or whatever it is actually does become a very reasonable size to use on a website or something of that nature. So we'll resize it to a 32 meg size, and then it's just going to go through a series of phases. It's going to take that initial image, it's going to resize it and make it larger. It's then going to convert it to that PNM intermediate format, and that's the raw format, and then it's going to go through that PNM format and figure out which bytes are safe and unsafe, and make it into an image that it can actually use. And then it comes up on the other side.